Hello, my name is Rafael from the Technical University of Munich, and I will be presenting our work on memory optimization in tinyML in the inference side and looking at fused tiling approaches to achieve this. So first of all, to shortly motivate the tinyML use case here with the note that we focus on inference, so just the pre-trained model, how to efficiently execute that on a target device when doing deployment for the device. So when moving from the cloud to the edge, you get improved communication demand. You might no longer need the communication. You have lower latency in your application to respond to certain tasks, and you don't need to send possibly sensitive information around the network. And especially for the very small use cases on small microcontrollers, extreme low edge, there have been many demonstrations that there are actually real use cases where this is very useful. Many of them were already mentioned today. So the challenge that we have been looking at was memory, because it is a major factor in very important metrics of power usage and cost. And there have been also quite a few topics touched on already today, like quantization achieves memory reduction, pruning, structured, unstructured pruning, and network architecture search are all methods to improve this memory metric. But I will point out that these are methods that will kind of change the behavior of your model, possibly reducing accuracy. And I want to present an alternative today that doesn't have this limitation. So what this targets is the intermediate buffers that are needed for the activations of a model. So I've given some examples here that show some popular models and the working memory sizes required for the different layers on the x-axis, and then how much memory is needed. And you will note that there are these peaks for very few layers or even just a single layer that require a lot of memory, working memory to store these activations. So one way to tackle this problem is to do this computation in a tiled fashion and then fusing operations to skip requiring these large buffers. So first of all, what is tiling in general? You've probably heard about it for loop tiling. This is a transformation path where you change the order of loops, how the loops are executed in order to exploit spatial or temporal locality of the data you're working with. So this shows a simple example where a two-dimensional loop could be computed in a different way, where you, instead of going through the x-axis and then the y-axis and so on, you compute these small tiles, so 3 by 3, and then going to the next 3 by 3. This is typically employed for performance optimization if you have some accelerator or a special memory hierarchy that benefits from this locality. Then this is a good optimization approach. But now we wanted to look at how can this be used for memory optimization. So that's where this fused tiling comes into play. I wanted to show this on a quick example here, a network showing the intermediate buffers with their size and then the operations between them. We have some very large intermediate buffer here that we want to avoid causing such a peak in memory usage, shown in this graph below. So this shows on the x-axis the different buffers that are required, and the width are their lifetimes. So you can see that this large buffer just contributes a lot to this total memory usage. And the idea is now to compute this large buffer in 2 tiles and then fuse it with the consecutive operation in order to decouple the lifetime of these 2 split buffers. So, for example, we start with the input, go through that tiled large buffer, continue onwards in a fused fashion to the next intermediate buffer, and then we can continue on the other partitions or multiple partitions to kind of have only one of these large partitioned buffers in memory at the same time. And in this case, we see some memory reduction that is achieved through this fused tiling. This is nothing new in particular. What we have called this, how it is typically done, is the fused feature map tiling. So for this, let's assume we have 3 intermediate buffers and with a large one in between, produced by 2 consecutive convolutional operations. So let's say first 8 output channels and then 2 output channels. And now we can do this fused tiling approach by basically splitting this intermediate buffer and then computing one tile, one partition first with the fused approach, because the convolution has this spatial locality property that actually these outputs, the red ones on the left, only need like the left inputs and so on, and this can be stacked. What I've also highlighted here is that there might actually be some overlap in these partitions with this purple area, because, well, this convolution, if it's 3 by 3, they both need these overlapping regions to be fused. And the major limitation here, what we have looked at, is that this doesn't really work when your outputs have a large or wide input dependency. So if there are some outputs that need a lot of inputs for its computation, for example, a convolution with a very large kernel size, or just fully connected layers are the extreme case, where you need all inputs, then this no longer works because you cannot really fuse in that case. However, we have shown that this is feasible if you restructure the operation a bit. So I will explain this fused depthwise tiling first on a fully connected layer to make it more clear. So let's say we have a similar architecture than our convolution that I've just shown, with a dense layer with 8 output neurons and then 2 output neurons. So we want to fuse these now. So we can first do a normal fully connected operation for the first layer. We just do 2 partitions, first 4 output neurons, then the second 4, and these are kind of independent. They just need all the 3 inputs, but we can fully compute them with the activation function and everything. But then for the second layer, we have this problem that we would need all these 8 inputs to fully compute them. However, we can still partially compute them by doing this sum of product of the partition that we are currently looking at. But then the outputs, they are not finalized, and an additional layer or step is needed that then merges these by just summing these partial values and then applying the activation function afterwards. The main benefit is here that we still can fuse here, and if there's a large size difference between this intermediate buffer and the last output buffer, this can save memory. So to quickly translate this to convolutions, given the same convolutional example from earlier, now instead of splitting by the neurons, we split across the feature maps. So we take one partition of feature maps of this large intermediate buffer and can compute them as normal. And then we can continue in a fused fashion to the output, again, only computing them partially, just these, the sum of product that is a part of it. And then finally, in some merge step, these could be recombined again. So to evaluate this, we found this is actually not too trivial, because a lot of factors go into the actual memory usage that you see in the end. And I will quickly outline our flow that we have developed to do this end-to-end deployment evaluation. So we have our input graph, that is just a neural network. We want to first schedule operations, so find some order of operations that are sensible for memory usage. This is, of course, if you have just a linear network, this is trivial, just the order of operations, but there might be more complex graphs, and especially when tiling comes into play, because this is an iterative approach, the scheduling matters a lot. So for example, if you have parallel paths of multiple operations, the order of execution matters for the peak memory usage. Another part is the layout planning. So actually, given this schedule of operations, you need to decide where these buffers are placed in memory. So given all the buffers, each buffer gets assigned an offset in memory where it is placed. And when lifetimes don't overlap, they may overlap in memory to save space. Then we select buffers that are relevant for this peak of memory, just looking at the buffers that contribute to this peak memory usage. And then going through them by looking at the largest first. We do this, what we call path discovery, which I will cover in more detail in the following slides. This basically selects tiling configurations that make most sense for this optimization. Then we have some tiling configurations, which we then use to transform the input graph in different variants that the path discovery has found. And then again, do the scheduling and layout planning to get actual layouts, which determine the size. And this size can then be used to check if we actually improved our memory usage, and then this can run iteratively to optimize further. This path discovery that we have developed uses a block-based methodical approach with the blocks shown in the top right. These blocks basically tell the algorithm how to match the type of tiling we apply to each operator. So let's say we have some untiled data flow graph here of lots of convolutions and one pooling operation. And this critical buffer selection selected this large 1000 buffer as kind of the most critical. Then we move up and down this data flow graph while matching the blocks to determine how this should be tiled. And there are multiple variants produced to compare the fused feature map tiling and the fused depthwise tiling. So let's say we start with the fused depthwise tiling. So this critical buffer that we selected becomes partitioned depthwise, PDD. And then we look for the convolution before, and the only block that matches this type ending with this type and supporting convolutions is the FDT fan out, so the kind of first operation of the fused depthwise tiling. And then when moving, actually this terminates the path because there can be nothing more, because this first fused depthwise tiling requires all the inputs, so we can't continue in this partitioned style anymore. And when we move downwards the data flow, this pooling is just a simple kind of element-wise operation, but there are some other operation types that are also just forwarding this partition. And then finally, when we reach another convolution, this is kind of the second part of this fused depthwise tiling. So now we also have to stop our split path at this point, because then we produce all the outputs and can't fuse any further. Just quickly compared that to the fused feature map tiling. Here we can continue a lot further because the dependencies are not so wide. We have this spatial locality of the convolutions. But actually we have to consider here that the overlaps might be introduced. So we actually produce different variants. So we make a very long split path, but also consider shorter paths because they might actually have lower memory since the overlaps are not so large. This was implemented in the Apache TVM machine learning compiler. And I actually put this open source today, so if you want to check it out, it is at this link. We looked at 7 quantized models, so 8 quantized for RISC-V, and the memory usage we just got from the compiled binary coming out of TVM, and the performance we estimated with just looking at the multiplication operations of the final model, because the optimizations for RISC-V and TVM were not yet very competitive. Yeah, and finally, we used TVM because it's very suitable for these complex transformations. Compare, for example, a TensorFlow Micro, where you have fixed operations for every fixed implementations for every operator. So it's very hard. You would need to do some kind of new compiler yourself to generate the new fused operations. The results I've shown here. In the first column, the 7 different models. Then you can see their untiled size. So this is just the normal deployment, the memory usage of them. Then using the fused feature map tiling, we found that for 2 models, this actually doesn't find any optimization because there are just not the right operation sequences to exploit there. And there we could find solutions when using this fused depthwise tiling. In one model, pretty significantly saving 76%. For the 5 other models, we could see that the memory was actually reduced pretty decently by the fused feature map tiling. However, this introduced some performance overhead because of the overlaps I've talked about. So, for example, for these 2 models highlighted in this slide, the overhead was significant in percent here, whereas the fused depthwise tiling doesn't really add any overhead because the splitting is kind of perfect, and the final addition you need to do is not significant compared to the more higher dimensional operations. So to summarize, we applied this fused depthwise tiling to DNN graphs to achieve memory optimization and build an end-to-end deployment flow that was able to evaluate this accurately. This approach reduces memory usage for some models where it was previously not possible, so finding new opportunities. And even for existing models or models that could be tiled by the existing methods for fused tiling, we could show that there might be a trade-off in terms of performance overhead compared to memory usage. And that's it from my side. Thank you very much.